So as a final topic, I will show you the basic things about optical fibers. And many of you may think that optical fibers are used for telecommunication, but actually there are many scientific purposes. For scientific purposes, optical fibers are used. And so it's good to know the very basics of the optical fiber things. And the very kind of basic things of to understand the basic things of the optical fiber, first we are going to think about a parallel plate, which means there's you can imagine that two of the plates, meaning the reflecting the light, keep the light inside here. And in here, it's kind of like the optical fiber. Then in this space, you have two different directions of the light you can find, right? So which is k vector k and k dash. And so we can imagine k equal k cosine theta and k sine theta, and then k dash means minus k cosine theta and k sine theta. So it's z direction is a propagation direction. So in this case, two electric field is E1 equal E0. Now we just simplify K equal 0 cosine K cosine theta Y plus K sine theta Z. And similarly, E2 equal E0, and similarly A0 cosine theta cosine minus K cosine theta Y plus K sine theta Z. So and then I'll assume Z equals 0, and then sum up the electric field, and then the electric field in total is, of course, 2E0 cosine K cosine theta Y. And when we think about the light intensity, which is E squared, and then it can be written like 4 0 squared cosine squared K cosine theta Y equal 1 plus cosine cosine twice of this K cosine theta Y. Right. So when you think about the E field, electric field, and intensity inside this waveguide, right? In this waveguide, and thinking about only the Y independence, it's sort of the oscillation field in the Y direction. we could find. So that's intensity, and you can think about the stripe in the y direction, which is inside the cosine to k cosine theta. And if you think about the waveguide thickness d equal to pi. And when we think about k equal lambda over 2 pi n, then now the d equal lambda over 2 n cosine theta. So now we can obtain the d. D is defined by the other parameters. Now the waveguide, the width of the waveguide must be an integral of this d value. So oh, I'm sorry, I made a mistake. So it's about this d is distance for making a oscillation pattern in the y direction, and actual waveguide is d, and this d must be some integral or multiple of d. So again, I corrected. So this d value is somehow this cosine oscillation period when this one satisfies the 2 pi value. And then this dimension of the waveguide can be defined by some multiple of d, and which is equal to m lambda over 2n cosine theta. So in any cases, probably when you use the optical fiber, so at first d is defined, right? So d has been decided, and then number of m and theta is kind of fixed due to depending on the wavelengths. And then what kind of light can be going into the optical fiber. So, and this m is called mode number of optical field inside the. And in the case of m equal 1, this field is the electric field in the y direction looks like this. And then m equal 2, you have 2 waves in a 3 case like this. So as increase mode number, so different type of mode you can observe. And keep in mind that when m is changed, since the d is same and lambda is also same, so actually the angle of the direction, so light direction angle is changed. So in some cases, some of the mode is really kind of going straight, but some of the mode is reflecting many times like this. So the speed or the travel time of the light is dependent on the mode. So that's one of the problem when you send the light by the optical fiber. And when you use optical fiber, another requirement condition is total reflection. Because when you use optical fiber, actually the inside, not only inside, but also outside, which is called clad, is also a transparent material sometimes. And if the light can go into the N2 side, the light, many during the many reflection, light just go out. So to stop this, you need to have a condition of the total reflection, which is we've already kind of studied in that sheet. Critical angle is sine inverse 2 and 1. So always the necessary condition is theta is larger than theta c. And also some of the technical issues when you use the optical fiber, you better know the structure of this. So the optical fiber is made of as I mentioned, a core and a clad layer. So core is the higher refractive index side, and then clad is lower, and light is confined in this region. And in the optical fiber, we sometimes use a normalized frequency, which is defined as 0 over 2 pi a and 1 square root of 2 delta. And then delta is defined as a difference of the refractive index. And this is a normalized frequency. And this is often used because how many modes are included in this optical fiber? By the way, this distance is A, so diameter. And ME, the mode number allowed in this optical fiber, you can roughly estimate like nu squared over 2. And as I mentioned in the previous slide, so if there are many modes, depending on the mode, the trouble time is different, because mode difference indicates different angle of the refraction. So in many scientific purposes, we usually use a single mode fiber, which means only a single type of angle of light can penetrate into this fiber. And you can control this by limiting this A value, so diameter. And there's some convenient way to know this. And if the nu is, the normalized nu is around 2.4, is a necessary condition, and which typically like 2A is like 5 micron, and so for the wavelength of 1 micron. So you have to prepare the core diameter very small, on the order of a few to several microns. And in this case, you can send only a single mode of the light. But again, you can imagine that this small region you have to put a light into, and that's reduce the light intensity, and also sometimes a problem of the optical alignment. So with that, a little bit detailed things, but let's finish about the optics things.